Okay, so we want to pick up where we left off yesterday, and we want to re-go over that last picture. Okay. So the final exam is going to be on Tuesday, June 9th. Okay. Unless that's an issue for everyone. Otherwise, I could do it the 9th or the 11th, but the 9th is what I was thinking. So, can't hear me? Hold on, let me exit and come back in. Because there was an issue with my audio earlier. Yes, it's going to be on Wiley. I'll be back in a second. Is the audio better? Can you all hear me now? Okay. Good. That means if you can't hear me, then it's on your end, not on mine. So let me get the camera back on. So yeah, about the final exam, everything will be the same. I'm not changing anything. It's just going to be online in the same way. It will cover a lot more chapters. It might be a little more intense. It might be a little harder to do, but that's okay. So I'll talk more about the final, I think, either during, after class or during break. But I want to cover this, our equilibrium. So as we saw, our conditions for equilibrium is that the net forces in the x and y directions have to be 0, and the net torque about the z-axis is going to be the 0 as well. Now, the directions here are true, but you can basically, you can make a plane, you can put your forces in an xy plane and make your torque perpendicular to those forces. In the case where this is more general, the same has to be true, but you could even have a f, an f net that the if you had a more generalized three-dimensional case, you could probably have fx, xy, and fz equal to 0, and then your torque about some perpendicular axis would be 0 as well. And I say that because you can certainly generalize this stuff. These are all vectors. They can have three-dimensional components. Okay. So, but for this class, we keep it simple, and we just put we'll have all our forces in an XY plane, and we'll have the torque going into or out of the board. And you can use either your right-hand rule to determine direction, or you can ask yourself, is it causing a clockwise or counterclockwise motion, with a counterclockwise motion being positive and a clockwise motion being negative. Now, another part of this that must be true or must be held up is that in order to be in static equilibrium, the linear momentum of the body must be 0 and the angular momentum of the body must be 0. So in order to be in static equilibrium, you have to have these additional constraints. All right. Now we went over a few easy examples, right? We did this checkpoint, and we talked about center of gravity. That was nice. But what we really wanted to do was go over these examples. So we drew the pictures of these examples to get all the forces in, right? You'll notice that all the forces here were very easy. They were all in the y direction. And what I want to do is I want to redo the figure and example here for the beam and the rope. Okay? So if you recall, we'll go to the drawing, right? We have some things to look at here. Okay, so there's a drawing. there's the picture. So let's look at the picture and let's look at all the things that are causing forces. All right, we have a force here from the cable. So right now we have a cable, we have a rope, and we have a beam. Right? So when we look at those three things, we have to ask ourselves, well, what are we talking about? You'll notice that we certainly can look at this tension here and look at the safe, right? Hold on, you can look at the safe and we can say that, okay, by summing the forces in the y direction for the safe, right? There's objects. We have tension in the rope minus big mg, and that's going to equal 0, right? And so if we have that big M, we automatically get something. So that's kind of nice. But you'll notice the problem isn't going to ask for something just that simple. They're going to want you to analyze the forces and torques on the beam. And in fact, the problem might be to find the, all the forces, either the tension in the cable or the forces on the hinge. All right, or to resolve all the forces in the problem. So if we look here, we want to draw our forces on the hinge. So you'll notice we have this force here from the hinge along the beam. Okay? And that we can break up into horizontal and vertical components, which is sort of obvious to do since we're doing a static equilibrium problem. We almost always want to just go to a directional graph. And they'll call this F vertical and F horizontal. And the magnitude of F hinge is just the square root of F vertical squared plus F horizontal squared. All right, is everyone with me so far? I'm just asking if you get what I've said now. Don't jump ahead of me, I guess is what I'm saying, because I'll get there. I just want to make sure that this part makes sense, what I've written so far. Okay, good. So now, that was the hard force, right? And looking at how the hinge works. But the hinge will give that force right along the beam. And then we have mg down. We have tension of the rope and tension of the cable. So we found the tension in the rope. Mg is known. This is a question mark. This is a question mark. And this is a question mark, right? And the tension will be this way. So now let's look at our static equilibrium equations, and we have 3 equations, and we'll see if we can effectively, and 3 unknowns, right? So we know we'll be able to sum the forces in X, we'll be able to sum the forces in Y, we'll be able to sum the torques. Okay? Now, let's go look at the next picture, which cleans up what we wrote, and we can see sort of our force diagram. I'm hesitant to call this a free body diagram because free body diagrams usually have forces acting on a point, even though all we have are forces here. We do have some other things, and we'll need to draw some other things on this diagram. Now, when we look here, you'll notice you have your forces, right? Labeled as so. Now, again, just to write it cleanly, I think my mouse might do a better job of making these sigmas. Sum of the forces in X, sum the forces in Y, and we'll need to sum the we'll need to sum the torques. Now, in order to sum the torques, we're missing one part, right? So we haven't done something yet, or you've done it in your head and didn't realize that you had to think about it. So we have to take the torque about a point, right? And the most natural point to take the torque about is the hinge, because we already know that the beam can rotate about the hinge. So that is a good natural point to take to have as your rotation. And also, in the torque equation, it automatically eliminates F and H, right? So that way we'll only have our one unknown, which would be TC. However, when we look at this, so let's look at the torque equation first. So we notice that if we're at this point, both F and V operate at a zero distance. So we have 0 plus 0, right? They don't do anything. And if you want to understand that, we can write down, because we're going to need our definition of torque frequently here, R cross F equals RF sine phi. You can make these magnitudes even if you'd like. And basically that's 0, right? So that's where you get these two yellow zeros at the top. But now when we do this, we have to remember that torque is equal to R cross F. Now in our previous examples with horizontal beams, all the angles are 90, sine 90 is 1. We don't have to worry about anything. But you'll notice here, right, we have a two-dimensional problem. So in order to look at in order to start evaluating these torques, we have to look at the R vector and look at the angle that the torque makes with the force. All right, so the R vector simply goes along in a straight line. So I'll draw it in red here along the beam. Right? And so we want to make some auxiliary lines at our forces of interest. We already have one at the end here, which is nice, but we do need to make one to help us understand sort of what it is we're seeing. So we'll make that line there. Now, to evaluate the next torque, right, we have to go here to mg, so it will be equal to so the torque will be equal to R cross mg, right, which will equal R mg sine phi. So we can see here that if we're given theta, right, our geometry tells us that this angle is theta. So for this particular, and this is a right angle. So for the mg part here, for this mg force, to look at the torque caused by this force, or at least the magnitude of it, we're going to have to look at r, which will be the length of the beam over 2, right? So we can call that L over 2 times mg times the sine of 90 plus theta, because that's the angle between the forces. The r vector goes this way, right? And that's the length at that point of the force. So now you have to ask yourself, you can use your right-hand rule, r cross this, it'll make it go in negative, so I'm expecting that this will cause a clockwise rotation, which it does, right? So it'll cause a clockwise rotation, so that will be negative. So let's go back to yellow. Be minus L over 2 It's probably better to put pi over 2 at this point. Yeah, Mina.
So, Professor, hi. So yesterday we're left at the discussion of the distance, how we take the distance.
Right.
So we left off at I was trying to understand like the distance here, L over 2. Now, what you wrote down with the sine 90 plus theta, that's from the torque relation. However, the distance L over 2 are when we taking it from the hinge, the point of rotation? Isn't
Yes.
that distance we take? So can
Yes.
I use the, hold on, let me take this and collect this. So let me pick up a color. I'm taking blue. So are we taking this distance
No.
or this distance?
No, neither. We're taking this distance. It's half the length of the beam.
Directly, like we don't
Yes.
have to take the okay.
Right. Because, and this would be so much easier to show in class, but the R vector is just the distance from the hinge, from the pivot point to where the force acts. That's it. Right?
Okay.
So we take that absolute distance from our pivot to where the force acts. And then that gives us our force vector, so it's sort of going that way, right? Going along the beam out. And so what we're doing here by extending it is not increasing the magnitude. We know the magnitude, it's L over 2, but this gives us the angle between that R vector and the force.
Okay, I see. I think that's where I got confused because I was thinking that we do not take the distance. We should think of the projection.
Well,
Be like
that's
the
another way.
horizontal.
You can do it using the moment arms. You can do it that way. I just don't, because again, it's like I'm stubborn and old at this point, so I just do it the way I like to do it.
Okay.
But you can take the perpendicular distance. You just have to do it correctly and take that perpendicular component, and then you don't have to worry about the angle so much. I'd rather just do the angle personally, because I can,
Okay.
and I think of it this way because in my mental process, I always try and focus on methods that I always know will work in any situation, right?
Mhm.
And so with this, it might be more tedious in some cases, but it's always going to work, and there's never a problem too complex for it to work. So so yeah, it's just a difference between fields. Like in engineering, they love lines of action and moment arms for some reason, and here I just like to use the straight torque, the R cross F. It might
All
be a
right,
little.
got it. Thank you, Professor.
You're welcome. I hope it makes a little more sense today. It should make more sense to everyone because now it's actually right.
It does. Thank you.
So all right. So when we go up here to our end point, we'll notice that we have two torques to look at. So let's do minus let's do minus L. Oh, that's going to be L over 1. Hold on. That's going to look funny. That's going to be L, right? And we're going to look at TR first, times TR, which we know is big MG, but that's okay. And then that's also going to be sine of 90 plus theta. And again, if theta is given, all this is known and we're okay. But then we also have the cable, and we're going to notice that's going to lead to a counterclockwise pull. And that is going to be, that's going to be a little harder to find the angle for, right? So that's going to be, I drew that wrong. So we know this is going to be a plus, and it's going to be L T cable and sine of an angle. So let's figure out the angle here. So this one angle is theta, right? This one is 90. And so we know phi here is, well, I'm gonna actually, we already have a phi defined, so I'm gonna name this something else. Let's pick another Greek letter. We're all a couple semesters away from quantum mechanics, so let's choose psi. So I'm just picking another angle here. Now I know that psi, I know that 90 plus theta plus psi equals 180, right? And so I can figure out that psi equals 90 minus theta. All right, so I'm going to write this as 90 minus theta. And again, right, everything's okay because given theta, we have to have theta here. We can set all of this equal to 0, which I'm going to do here. And then that simplifies things considerably because as we've seen before, the actual length of the beam isn't going to matter much. So we can rewrite this as, I'll rewrite it over here. All the L's, I'll get rid of all the L's. And I can rewrite this as T2 sine 90 minus theta is going to be equal to mg plus big mg times sine 90 plus theta. Okay? So there's a few ways to simplify this even further. You can factor out the g and make it even more compact. But what you can see here is that, oh, that's not supposed to be T2. It's supposed to be a C. What you can see now, though, is that everything here is known on the right-hand side of the equation. And we only have the one equation. So we have one equation and one unknown for TC. So now let's look at this summing the forces. The summing the forces will be easier, but before we move on to that, is everyone clear on the torques and what you need to do? Because the torque part is counterintuitive. I hope you kind of found that. I hope you kind of saw that maybe looking at some problems last night or some homework problems. What are we thinking here? Again, I'm not doing the forces yet. I'm just looking at the torques.
Professor?
Yeah.
I have issues with determining the angle between the axis of rotation and the force.
The axis. So which angle are we concerned about?
Both angles, the 90 plus theta.
The 90 plus theta?
Yes.
Oh, okay. So when we look at that, if we look here, this angle is given in the problem, right? So we take that as just the word of the problem gospel, if you will. So we know here, when we look at this force, this is the first one we're going to look at, mg is pointing down, right? Now our geometry will tell us that this parallel line is going to be parallel to this line. I may have not drawn it parallel, but it's supposed to be parallel, right? And so if these two lines are parallel, because I can see now that it's not parallel, but it's supposed to be parallel. If that's true, then these opposite angles have to be congruent. We know that from geometry.
Yes.
And then, so we're looking now at the distance that the r vector, which goes along the beam, makes with the force little mg from the beam, right? So that angle is going to be this angle I just drew here. All right, so
Okay.
that angle is composed of two subangles, right? One is theta, which is given, and one is 90. So
Right.
that angle, or phi, you could say here, right, that phi is equal to 90 plus theta. And that's why I plug it in here.
We
Now you'll
can take
notice,
the other angle, which is theta, which is the opposite of, let me see, which is this one.
we've already defined theta, but you'll notice it can't be theta because otherwise the force would go horizontally. So, but the force is going vertically down. So you have to add that 90 degrees.
Right.
Hmm?
But it can't be this one. Right, just this one, the angle.
It can't just be theta.
Right, which is theta, yeah.
Yeah, it can't just be theta because if it were theta, in order for, let's look at a triangle independent. Let's look at a separate triangle. Just give me a minute to draw one. So it's a similar idea, but maybe not exact. You just don't want to mess it up. All right, that's a good right triangle, right? So if we just use the angle 30, the implication would be, right, we have an r vector going along the triangle. So in order for the angle to be theta, the force would have to be moving along the horizontal axis, because then the angle between these two vectors would then be theta. But that's not the case. mg doesn't point along this horizontal axis, it points down. So the angle
Got it.
between
Thank you so much. Yeah.
has to be theta plus 90. Okay, good. You got it?
It's just a matter of direction because R is directed to the right,
Yeah,
up to the right.
right. You have to, the magnitude ends here, but you have to move the vector abstractly to figure out the direction, because you need to be, in order to figure out the angle between two vectors, they have to be tail to tail.
I see. Thank you so much.
You're welcome. Okay, good question. Any other thoughts, anger? Okay, so moving on to the forces. This is the easier part. I'll keep it in red. Why not? It'll make it easier to distinguish from all this nonsense. So if we look here, right, we can just go by the forces and look and see what has a y component. You'll notice we have three forces with a y component. So we have Fv is equal to, getting ahead of myself. All we have to do is go through and catalog them and look at their directions. We have Fv minus little mg minus tr equals 0, right? So we know tr, we know mg, we can actually find Fv right away. So that's nothing new that we have to do, and that might have been the easiest one to start with, but that's okay. We're just being systematic. So if we look in the x direction, you'll notice we have Fh minus Tc equals 0. And now here, this is where things get a little complicated, because in order to, so the good news is once you find Tc, you find Fh, so that's not bad. But that being said, it's you have to defer back to this torque equation to get Tc, right? So Tc will give you T horizontal, and then you can, or F horizontal, and you can just solve for F vertical directly. Okay? So I hope that breakdown makes some sense. I want you all to, take a minute or two with it and look at it, and also, did you guys pick any? If you picked any homework problems from this set to do, let me know. And I'll get my Wiley textbook ready so that I know what problem you're actually talking about, so I can read it. All right. Okay. So, questions? And did anyone pick a homework problem to go over? These can be kind of fun. Yeah, Artin.
Yes, on the sum of torques, that is L over 2.
Where's what?
The torques is L over 2 mg sinus theta 90 plus theta. What we discharge
So it's L over 2.
What happened to 2?
So you're asking about the mg torque?
Yes.
Yes. So that's L over 2 mg sine 90 plus theta.
Yes.
I crossed out the L's because there's an L in each term, and the sum of the torques is equal to 0.
Yes.
So that let me cross out the L's.
What about the 2? One half.
Well, there's not a 1/2 in every term. That doesn't cancel.
Yeah, but it's not in the bottom equation though.
Oh, it's not in the bottom equation? That means I just left it off. There we go.
There we go. Now we're good.
Good. All right. That means Artin, I just I forgot to include it.
I got you.
Yeah, that's what happened there. Good catch. Thank you. So if you want, since I've sort of just gone through and picked one at random. I don't know if I assigned it or not. But we can, you know. I see. I see what's going on here. Hold on. Everything's disappearing on my computer right now, which is unfortunate. There we go. Okay. Yeah, the computer is just not really cooperating, unfortunately. Oh, geez, which window do I pick here? There we go. Okay. All right. So I need to, okay, the computer, I feel like I'm an old person. I've been using computers my whole life and like it's not working. It just keeps maximizing, and I can't see. Okay, this is annoying. I need to resize you because you're being ridiculous. So I think I assigned problem 21. So I think we could do that one. And be okay. So I think the best way to do this is what I did in the other class is I made a PowerPoint slide with the picture from the problem, with the problem. So I'm gonna do that really quick. I was sort of hoping someone would pick your own problem, but that's okay. File, new slide. Here we go. Okay. Oh, hold on. All right. Chapter 12, yeah. I'm already doing this one though, so we've passed the point of picking, I guess you can say, because I'm already almost done with the slide. I don't want to have to look again because I'm fundamentally slightly lazy. Not terribly lazy, but slightly. Or at least not to want to do this process again, because it's file. This PC. We'll call this chapter 12 problem. All right, so let's go. I'm going to stop sharing this, so hopefully have whatever you need written down. And we're going to go to files. There we go. All right, so we gotta wait a little bit for that to convert. Sorry. And there we go. So we will. There we go. So now we have a problem. Okay, so let's work on this one. So we have a system here is in equilibrium. We have a concrete block of mass 225 kilograms that hangs from the end of the uniform strut of a mass of 45 kilograms. A cable runs from the ground over the top of the strut and down the block. All right, this would be too hard to draw on our own, I think. I'm glad we have the picture. Holding the block in place. So we have a block, a cable with tension, and we have what is called a strut. This is what we'll call our beam. And we have a hinge. So we're given angles phi and theta. So we have these two angles, right? These are given in the problem. We have the mass of the block. And we have the mass of the strut. And we want to find the tension in the cable and the horizontal and vertical components on the force on the strut. So remember, we'll have horizontal and vertical components and this T here. Okay, so that's three things we need to find. We have three equations. We should be good. So now what I want you to do on your own for a little bit, I want you to work on this, and I want you to I'm tempted, if I knew how to really do the small group thing, I'd put you on small groups to work on it. But I want you to try working on this on your own for about 5 minutes. See if you can get started. But then I'll open it up for the class to sort of have a discussion on how to do it. I want you to try and think your way through this problem. And this is one of the more important problems for you engineers because you'll be doing stuff like this all the time in statics. All right? It'll be more obnoxious there, I promise you. So give it a try. Again, like I said, we'll go over it. I just really want you to push and get frustrated. And like I said, the goal is to try and identify that for you. We will absolutely go over it, though. That's going to happen. So don't worry. I'm not going to go over it. But I want you to try it a little bit, and I want to sort of work through it together. Okay? So take 5 minutes to work individually, and then take another 5 minutes to sort of confer with each other. And while you're doing that, it's feel free to ask a question too. But try and work this out. And I think we can. We saw that there were a lot of details to get caught up with. Identifying the R vector correctly, keeping track of all the algebra. It's tough. So I'll let you do that. Mm. Okay, how's it going? Did you all start talking? I didn't hear people talking to each other, and I didn't see any chats going on. So what are you thinking? So what I think we will do is, no, I'll go over the problem and then we'll go on break. I thought I would just take a break, but we'll go over the problem first. So this actually looks a lot like the example. It's just that the angles don't quite line up as nice. So the first thing to do is to sort of figure out which angles matter. All right, so let's delete this stuff. And we know we're going to have our R vector go along the strut. So we're going to put our dots where our forces act. All right, so we'll have mg acting here, going down. And then we have this one acting vertically to the strut. Oh, hold on. I want to make a cleaner line. I want it to be vertical. Now, we want to know the angle between, so we want to see where the forces are acting. So we have these two vertical forces, and we have this angle here where the tension is pulling. So we'll have that angle, I guess we could call that, we'll call this one alpha, and we can call the angle we want here gamma, which will ultimately be the angle between this radial vector and these vertical force vectors. So this is the other way to look at it. You know, they're supplementary angles, so all the math should work out the same. But that's the it's, you know, it's just looking at it from two different points of view. But right, going this way or going this way. You could also use the 90 plus theta. But you'll notice they're related because this angle is theta with this right angle, right? So this is theta, that makes this gamma. So you can look at gamma, so we have our two angles gamma, which will just make our lives a little easier, in alpha. So alpha is so gamma is going to be equal to 90 minus theta, right? That's going to equal 45 degrees because theta is equal to 45, right? And then alpha, here we have 45, we have this big angle here, so we have to look at is equal to 180 minus 45 Yeah, Artin.
You can do it like 90 minus theta. We got a 60 degrees angle.
You do not. Well, again, it's you ultimately want the angle. You ultimately want the angle between the force vector, the direction of the boom, and these
Yeah.
vertical forces.
Yeah,
right?
it comes out to 15 degrees, I think.
Oh, the alpha? Yeah, no, it is, but I'm just showing everyone how to do it.
I mean, it's geometry anyway. Sorry.
Yeah. Yeah, no problem. So you're right though, Artin. It absolutely comes out to 15 degrees. But if you add alpha plus phi plus 180 minus theta, that's what I was trying to get to. Alpha is going to equal, that should all equal 180, right? So, right, because that's 180 minus theta plus phi plus alpha. That should all equal 180 because the interior angles have to line up. So 180 minus 180. So you get alpha Okay, accidentally threw myself out there. Sorry about that. Hold on. I need the email to stop. All right. Okay, the email is driving me crazy here. It just keeps coming. Stop coming. We can't get to my menu. Okay. So, sorry about that. Let me get back on the video. Okay. So we're still going. So, right. So we can look here and go get that alpha plus what did I call that? It's alpha plus phi minus theta has to equal 0. And so we know that this one is, so alpha is going to be equal to theta minus phi, and that's going to be equal to 45 minus 30, and R10 got it exactly right, is equal to 15 degrees. So I'm going over this because we seem to have some issues about the angles and why we picked them. So I wanted everyone to be crystal clear on how to do it and what to do it. You have to recall some of your rules from geometry, which are that the sum of the angles of a triangle are 180 degrees, right? And this is a half bit of work. I'm going to erase all this soon. So and yeah, and that we're finding creative ways to get the angle between this strut and the force, right? So so again, that will give us just the raw angle between these two vectors that we can use, and that should make the calculation easier than writing 90 plus theta and all that stuff. So let's get going on summing these torques. Okay? So, what did you get? I think that's correct. So let's look, but let's get there first. So let's delete the angle stuff. So now we're gonna look at our two angles. We're gonna call this one beta and this one alpha. Or no, we call this gamma, sorry. Gamma. Okay, and we know that alpha equals 15 degrees. Gamma equals 45 degrees. So all that work is to make summing the torques about the hinge a lot easier, all right? So let's do that on this down here. So we're going to sum the torques first, all right? And the hinge forces will cancel. And we have, just like last time, we have these two forces will lead to clockwise motion, and the tension force will be positive. So we'll write the tension one first. So we can write L times T times the sine of alpha, right? Makes this a little easier, minus L over 2 mg sine of beta, or sine of gamma, rather. I should have picked beta because alpha and gamma. I'm going to go into the problem here, minus L big mg. That's also going to be sine beta. All right, and that's all going to equal 0. So again, like before, the L's go away, and we get T equals it's going to be m over 2 plus m. So that's a little m. That's a big M. And again, we cross these L's out, just so if you're wondering where those went. And that's going to be sine beta, sine gamma, over sine alpha. All right. So Archon looks like he already plugged it in and got 6,300. So let me see if that is the right number. If everyone agrees with them, I'm going to say that's probably okay. And I just have to Wiley plus this because I'm not going to calculate it all out. And yep, that looks right. 6,630. That'll do it. So we got the tension right. Wait. Oh, but I forgot something, didn't I? Can anyone tell me what I messed up on here? What's this whole thing missing? This is as it stands right now, the tension is incorrect. I'm going to make it look nicer. I'm going to move stuff while you guys tell me what I messed up. Yep, you got it. Let me make this look prettier, though. Okay? So, when we do this now, though, unlike the last part, T, you'll notice here, is going to have both X and Y components. So that will make this a little more interesting to solve. But before we move on there, I want you to double check the torque part, and I want you to make sure that it makes sense to you. All right. So now we want to look at the sum of the forces in the x direction. So we'll look here, the tension on the strut. How did I get sine beta? From torque. Sine B. I don't have a B. I have a gamma. I've been saying beta by mistake because it's the next one out after alpha. And you can see that the two angles are given here, 15 degrees, 45 degrees. I went through how to get those angles pretty painstakingly, Chica. So I'm going to tell you to refer to the video before going over that again, because that was a lot. But basically, you have to add up all these angles, and the strut is pulling down this way. So we're going to, this vertical distance, the forces, you'll have an angle between the strut and these vertical forces. That's what we're calling beta, or gamma rather, which you can see right here. It comes right here. And then you have this alpha here. Remember, the angle here for torque is not a component angle. It's not based on horizontal and vertical. It's based on the angle between the force and the radial vector. Okay? So that's going to play a major role. When we do our x components, though, when we look at a force going through, right? The force, the tension on the strut, we'll be pointing in the negative x direction, and it'll make this angle, this 30-degree angle with the horizontal. So Fx is going to equal minus minus t cosine of minus 30. And that's going to be the same as t of 30 because the cosine is positive in the fourth quadrant. So, and then there's going to be the plus F horizontal from the strut, and that's going to equal 0. So F horizontal is going to equal t cosine 30. So we have that. I'm not sure if I answered your question, Chica, but yeah, did the best I could there. Again, how we get these particular angles, we have to go through. Cosine 30, sine 60, I think you're going to kind of get the same thing. So I'm just looking at it from a triangle perspective, just what angle it makes at 30, and saying, oh, okay, it's the x component is the adjacent over the hypotenuse. So, and then I have 30. But if you use 60, then yeah, you'll get the same thing. And then let's see here. If we do in the y direction, right? The sum of the forces in the y direction. will be equal to, again, we're not being pulled up, we're being pulled down, so we'll have here minus little mg minus big mg, right, for the block, and then we will have minus t sine 30. And that will equal 0. Okay? And then all we have to do is solve for, oh, no. Bad, Professor Toland. He's going a little crazy here. That's all right. It's just the end of the semester. I have to include the darn thing we're solving for, otherwise none of this makes sense. Plus f horizontal or vertical. That's going to equal 0. And now I can just move all these minus signs very, very easily to the other side. That's the issue of not writing this stuff down explicitly. And that's why I forgot it. That's why I tell you to draw pictures. No, this is f horizontal. Okay, the dysgraphia is having a bad day today. F equals. I just have to write this stuff a little slowly because my brain is futzing out on me. Okay? And that's pretty much it. So let me see. Let me look on the notes again that I have for the numbers for this particular problem. So I get 5. Yeah, that's about right. I get 5.74 with sig figs, but that's close enough. And then, yeah, good, Artin. All right. So that is basically, you can see, I'm hopefully you're seeing that it's different, but it's the same, right? And you'll find that with all of these. It's just a matter of sort of chugging through, getting all your angles right, being sure you label all your forces, and then once you have all of that figured out, then the torques and the forces become easy. If you don't have that figured out, it becomes pretty darn difficult. So with that being said, let's take our 15-minute break. We'll come back at around 2:30, and I'll introduce us to the concepts of the next chapter, which is kind of perfect because I want to get started on gravity and talking about it, and then we can wrap it up and get a little deeper into it next time. So I'll just kind of talk about it and talk a little bit about gravity and why it's important. Okay? All right, so I'll see you all at about 2:30. I will be away from the computer. I'm back. All right, so now we are going to switch gears to a topic that is pretty near and dear to pretty much every physicist's heart, which is gravity. Now you may be saying, Professor Toland, we did gravity way back in March sometime. What are we doing gravity again? Well, the gravity we looked at before is we sort of identified gravity on Earth and identified it as this force that's pulling towards us. But it actually, gravity was developed not to study, our dynamical, everyday universe, but it was actually invented to study planetary motion. And I want to start a little bit with planetary motion and sort of what the ideas were that would lead people to, what the problems were and why gravity itself would be formed. Because gravity as structured is not a relationship between a person and the Earth, but a relationship between any two objects in the universe. So let's get to the sharing file fun time. And we're just going to kind of talk about it and go through an overview. We might do some of the qualitative checkpoints, but we'll go through the basics. So we'll go through section 13.1 definitely, and then talk about, do some expansion on we'll cover a little bit of the other stuff. We'll cover section 13.2 in detail and 13.3 very likely on next Thursday. But for now, we'll just talk about gravitation. So now, again, it says, some of this is misleading, but we'll talk about it. So again, gravitational attraction as formed by Newton, and let's take a look at some of the major questions before we go in there, because I was about to just start talking. So let me go to. Let me see if I have a blankish slide. I'll use the front slide. So originally, how did someone come up with gravity, and why, and in what context? So you've heard the story about Newton and the apple falling, but why was that significant to him? Well, at the time, basically the major argument going on in science at the time that was very clearly being settled by the time Newton came around was whether the Earth was in the center of the universe or the sun was at the center of the universe. Now keep in mind the telescope had just been invented, giving us experimental evidence for the fact that the sun would indeed be the center of at least our local solar system, if not universe, what they would have called it at the time. And you have to, and you might, it's easy to sort of dismiss Earth-centric people, that the Earth is the center of the universe, as some sort of crazy divine type of thought, but it's based on data. Now, of course, once better instruments come along, data does show that the Earth goes around the sun. The sun is the central object, and in fact, Newton's model the significance of Newton's model is that he was able to incorporate several experimental results into a theoretical model, thus creating what's really the first scientific theory. So in some ways, in many reasons, this is why Newton will rise to the top of most influential mathematician and scientist, or physicist at least, of all time, is because by creating his theory of gravitation, he birthed the modern scientific theory. And what his theory did was, or his laws of motion they were called at the time, but today it's called Newton's theory of gravity, is he was able to collect seemingly, he was able to collect and define relationships between what were at the time unrelated empirical statements. And so let's talk a little bit about those. So when you're looking at the stars or the night sky, right, what you see is is thousands of stars, like 2,000 or 3,000 stars, and all the stars behave very nicely, and they sort of move through the night in these nice, well-defined circles. There are 5 objects in the sky. Well, there's 6 objects in the sky. One is the moon, although the moon behaves pretty well. But there's 5 objects that you can see with your naked eye that just don't behave like the other stars. So what happens with those is they look like they're moving in a circle, and then they move backwards, and then they move forward again in their circular path. Like say they're going in this path when we see them. So they have these epicycle rings. And so I want you to imagine you have a data set of 2005 points. Yeah, retrograde motion. That they have, that's what I'm describing. It's called retrograde motion. And these epicyclar, they call these epicycles or retrograde loops. So imagine you have 2005 data points, and 2,000 points agree with your model and 5 don't. If you're thinking to yourself, well, we can just throw out those 5 points, congratulations, you have just proven with your model that the Earth is indeed the center of the solar system. And there are reasons for this. One of the major reasons to think this is that people did question, well, maybe the sun is at the center, and a good reason to do that is it solves the epicycle problem, right? If the sun's at the center, we're just moving at a different rate than other planets, so we see them go through retrograde motion because we spin around faster. And you might be thinking, well, duh, well, why not put the sun at the center? It's easier. Now there's a problem with your 2,000 other data points, which is that you don't see what's called parallax. So I want you to put your finger by your eye and close one eye and blink back and forth. And you notice that your finger will appear to shift position, right? If you call one eye January and the other one July, that's what you expect to see with stars at relative distances from each other. And that wasn't seen with the naked eye. People looked for literally thousands of years and never detected this stellar parallax. That was a big problem. The enormous distances and vastness of space was beyond comprehension, and it was really Galileo who invented the telescope. Using the telescope for astronomy rather, and pointing them upwards, he was able to show that one, Jupiter had moons, and so not everything rotated around the Earth. He was also able to show that the Milky Way he could resolve individual stars, which meant that the distances were much bigger than he previously conceptualized. And he also showed that what's the other one? Milky Way, Jupiter. There's a third one. There's a third thing he showed. Phases of Venus. Yeah, no, that's true. He did see the phases of Venus, which proved that Venus was orbiting the sun. That is true. That wasn't what I was thinking of, though. He showed something else, but I'm going to go with phases of Venus because that one's probably better. So what that means is that so the phases of Venus, they observed that Venus can look crescent, half, or full like the moon, proved that it orbited the sun, not the Earth. So basically, Galileo experimentally showed that the Earth was not at the center of the solar system. But people kept trying to hold on to it. Oh, right, this is what I was going to say. Eventually, the telescope was able to show that the existence of stellar parallax, this back and forth motion. Okay, so once you could detect the parallax, there's no reason to think the Earth is at the center at all. Because now, in fact, the Earth at the center doesn't explain any of the points at all, and the sun being at the center explains every point. And that's how good science goes. But again, Newton modernized science by formulating a whole theoretical model to explain all of these observations. And that is his universal law of gravitation, his universal theory of gravitation. So let's sort of jump into it. I like that they use the word stuff a lot, so I'll want to read that. So gravitational attraction depends on the amount of stuff or mass an object is made of. All right? So the Earth has lots of stuff, and it produces, it says a large attraction. It's an attraction big enough to keep you on it. So gravity is always attractive. It's never repulsive. This will be important as you leave the confines of, physics 1 and get to physics 2, where you will deal with repulsive and attractive forces. So what Newton realized is that the attraction was responsible for maintaining the orbits of celestial bodies, and Newton's law of gravitation defines the strength of the attractive force between any two particles. Right, by stuff they mean the matter, right, the amount of matter something is made of, or mass. Now for people on Earth, right, or for an apple on Earth, the force, the universal force of gravitation, which we haven't seen yet, so it's not going to make sense, is 0.8 newtons. But for two people, it's less than 1 micronewton. Because you have to ask yourself, Newton's law of gravitation says that every object in the universe is attracted to every other object in the universe. So it's fair to ask, why isn't everything crunching in on itself, right? 1, there are other forces of nature, and 2, those forces are quite small. And we want to see why they're small, and that will be given by our expression of Newton's law of universal gravitation. You can see that the force between any two objects, the gravitational force in a vacuum, it's the best way to look at this, is going to be equal to the product of their two masses over the radius of the distance between those two masses squared times this constant of nature g. Now there are 3 constants, main constants of nature. All right, one is g. This is the physics 1 constant. The speed of light, c, is the physics 2 constant. And h, or h bar, is the physics 3 constant. So freshman physics can sort of be thought of as building up to each of these constants. Okay? So you'll notice, though, that g is very small. So when you're multiplying, say, 2 masses, 1 kilogram mass is separated by a meter, and you get 1 for everything, right? You have to scale that by 10 to the minus 6.67 times 10 to the minus 11. Now, interestingly, g was the first discovered constant of nature, and it is the least precisely measured. All right, you can't get much better than a 3rd or 4th significant figure, whereas c and h can be measured to 10 or 11, sometimes even 12 decimal places. Okay, so the precision of those other 2 constants is far greater. Now in vector form, you'll notice that you have the r hat direction. That should mean be careful, because r hats, theta hats, and phi hats make things difficult. But it's important. It's important to get a sense of what we're talking about, though, when we apply Newton's law of universal gravitation, because it may not be clear from the explanation, but you have to apply it between 2 bodies. And the force you get is going to be this reaction force, right? So you get F1 on 2 and F2 on 1 from this universal law of gravitation. All right? Now, this chapter it's interesting because we had our first big engineering application to the physics we've learned, but now we have our first big science application to the physics we've learned. And gravity is the first stepping stone. This universal law of gravitation is the first stepping stone to one of the big questions of physics, which is to explain how the universe works. You'll notice I said how, not why. Physics very rarely answers a why question, but it has tons of answers for how. So for instance, we don't know why the universe came into being, but we have a pretty good idea the steps it went through and we have models that go back to an insanely small amount of time before our physics breaks down, and a lot of weird things happening. And we have a lot of evidence for that too. But gravity, when you think about, gravity was invented to answer and understand why things moved in the universe. And it's the study of gravity that has led us through history to revise our understanding of the universe. So to briefly sort of outline it, just the major developments, just the hits, if you will. You had gravity from Newton, and then later on down the road, you had E&M was developed, electricity and magnetism. But electricity and magnetism was not compatible with gravity. All right, so that segued into special relativity. And it was to answer that problem that Einstein came up with special relativity. I'm going to call it SR because it's I'm going to redo this, but with the E&M type things, because I've noticed I'm losing space here. So we have Newton's gravity, which I'll call N-grav. And then later came E&M. Like I said, those were incompatible. And that the questions of that incompatibility led to the formation of special relativity. And then in order to, and that answered questions, that made E&M compatible with Galileo, but in order to make it compatible with Newton, Einstein had to develop general relativity, or GR. Okay? And general relativity helps us, or gives us the framework to describe things like black holes, phenomena we see in the galactic and cosmic scale of the universe, and for very large structures and very large scales of the universe, general relativity makes many phenomenally tested predictions and verified predictions. But on E&M, there then came something called thermostat. And then that was explaining gases and things like that. That came later. And from there, that led to the issues in thermodynamics, led to the development of quantum mechanics. And then quantum mechanics worked but did not incorporate E&M. So the E&M had to come in and create quantum electrodynamics. Or actually, I'm going to call this quantum electrodynamics is correct, but basically there's an evolution of quantum theory to quantum field theory. And that started with that electrodynamics, QFT, and general relativity. And now the big picture in physics, right, is to somehow get to a new theory in which these two play well. These are not compatible theories at the moment. General relativity is a model of the universe that assumes the universe is continuous, and quantum field theory demands the universe be discrete. Those two ideas, you can be one or the other, you can't be both, or at least not any way we understand. So from that sense, that's where sort of all of physics is going. This is sort of physics in a nutshell, if you will. But the important thing to understand is that unlike, and what Newton's theory did is that, so physics 1, I'll put it in different colors. Physics 1 sort of builds us up to understand the importance, because we did the importance of gravity, right? That's physics 1. Physics 2 is E&M, and then special relativity and quantum mechanics get covered in physics 3, or modern physics. So dark matter is described by general relativity, but we don't have a particle, a discrete version to describe it. Yeah, so that's where let me get the whole question. Yeah, basically dark matter right now is in the realm of general relativity, But the idea is to look for a particle model, so a quantum model of dark matter, to see if that will lead to insights into this question mark. Black holes are firmly within the realm of GR. So yeah, we use quantum mechanics, helps us describe what a black hole is, because basically when the rules of dead stars violate quantum physics, that gets us to the question mark area, where we don't know what's going on. But essentially, even though you have refinements on Newton, when you make all of these things look like a physics 1 problem, you need to get physics 1 answers. So Newton created this foundational block, which is what we learn about here, that leads to everything else. And by taking these theories as far as they can go, you get new theories and new understanding about the universe. And when it gets to like why I studied, because I often say that physics is a study of motion, but when people ask, well, why are you a physicist? And it's like, well, motion is interesting. I enjoy it, but really understanding how the universe works and how things can happen in the universe, that's why I study physics. That's what I get out of it, and why I think it's an interesting subject. And even if you're not going to be a scientist, I think it's a good liberal art for our engineering majors to think about a little bit. Plus, like I said, it makes the rules for what you can and cannot engineer. And unlike a lot of other liberal arts, it's very rigorously mathematically developed, so you can understand why those limitations exist. So let's take a look at some of these examples of how they attract. All right, so we can see here it's that we have a particle 1 and particle 2, and we're just going to concentrate on particle 1. So that's one thing you'll notice, all right, is that particle 1, you'll pick a particle, that will be your reference particle, and you can draw the unit vector with its tail on particle 1, and you can show that it's being attracted to particle 2. All right, so the unit vector, of course, r hat, will only have that length of 1 from particle 2 and point in that direction. And that's an important thing to realize about r hat without getting into complicated spherical vector spaces, is that we're pointing to our second mass. All right, so now we can use some symmetries to make our life easier. The first one, in looking at different geometries. So a uniform spherical shell of matter attracts a particle that is outside the shell, as if the shell's mass were concentrated at the center. So let's visualize that. So I want you to imagine, I don't know where that coffee's coming from. I want you to imagine a spherical shell, all right? So it's not full, it's just a shell, and this mass outside it. So that's M1 and M2. Basically, you can treat this. An equivalent problem is to shrink all of the shell, all of that shell, to a point, and put the distance between the center of, to shrink all of this shell to its center at a point, like so. And then we have this the same distance away. So we'll call that D, D. And these are equivalent problems. All right? That's if the shell is outside, the particle 2 is outside the spherical shell. If it's inside, it's a little harder, but it is not completely unmanageable. All right? So, so if we look here, the shell theorem can describe gravitational attraction for objects. And basically, the big weird thing to look at here is that you can think of Earth as a nesting of shells. So we feel Earth's mass as if it were all located at the center. And the reason we think of it as a nesting of shells is because that will help us conceptualize what goes on inside the Earth, as we, if we were to jump into a giant hole, for instance, and wouldn't get burned up going down. We'll see that the gravity below us will be affecting us, but the gravity above us will symmetrically cancel out. So again, these gravitational forces form Newton's third law pairs, and the Earth and apple in this situation are both 0.8 newtons, but you'll notice the acceleration of the apple is 9.8 meters per second squared, but the acceleration of the Earth is there, but it is very, very small. In fact, you can figure it out by just you know, we can divide 0.8 by 10 to the 26 to get something here. I think we get equals 10 to the minus 27th, probably something like that. So keep in mind that in the universe, there have only been 10 to the 18th seconds since the conception of the universe. So to get, if this were in meters per second, to accelerate the Earth up to 1 meter per second, the force would have to be acting continuously for almost 1 trillion times the age of the universe for the Earth to be appreciably accelerated. So, but the forces are the same, right? So there you go. Now, so they did it here, right? So it's nearly 10 meters per second and nearly 10 to the minus 25 meters per second. Still, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so 10 million age of the universe. All right, because I was off by 2 orders of magnitude. I guess a billion would have been 9 orders of magnitude. That's all right. It's the end of the week. I'm getting tired. I can mess up a billion and a million. But you can see the picture here of the apple Earth system and the comparison. This is the acceleration of Earth due to the apple falling down, and this is the acceleration of the apple. All right. So the Earth is attracted to the apple, but its acceleration is very, very slow. So let's do this checkpoint, and then I think we'll call it a day. So a particle is to be placed in turn outside 4 objects, each of mass m: a large uniform sphere, a large uniform spherical shell, a small uniform solid sphere, and a small uniform shell. In each situation, the distance between the particle and the center of the object is d. So we want to rank the objects according to the magnitude of the gravitational force they exert on the particle the greatest. All right? So keep in mind a few things here. F equals G, M1, M2 over R squared. All right? And read it carefully. And remember what we said about shells. What are you all thinking? Yeah, Mina.
I'm just trying to clarify here
That's
because it
okay.
says,
These are meant to be unclear, these checkpoints sometimes, I think. So go for it.
yeah, so we have four objects, right? We have the large uniform solid sphere, a
Yep.
large uniform spherical cell, right?
Yep.
So those two, do they even have the same radius?
No, I wouldn't think so. I think large and small. But remember, the thing here is that the particle is to be placed outside of the four objects. The outside here is the key. And remember what we said about shells and being outside a sphere, a spherical shell or solid sphere, as opposed to inside one. Or to thinking of the Earth or a solid sphere as nested shells. I think I missed one.
I think the concept of the shell itself, the way you said in nested cells, it's kind of confusing. Can you provide a little bit of clarification of the theory of how a nested cell is looking like visually? What is exactly?
I'm trying to think of how to draw it, and I'm not very good at drawing it. I'm gonna find a picture online and put a link in the chat, because
Okay.
that's the only way to do these things. Because the internet or the share screen feature is stupid.
No problem.
I have no
Thanks
other way
for
to
the
say
answer.
it. Nested shells. It's important to see. I can see that being confusing, because like I couldn't draw it to save my life.
But for the sake of answering, since you said outside of the cell or whatever, won't it be the same? I'm thinking about them because they have the same mass, all of them.
So if you can imagine, hold on, I don't know why they don't put it in here. I hate how everyone tries to make everything either way too. Here we go. So I'm gonna link a star chart, and you could almost think of each colored layer. Copy link. Hold on. Yeah. Okay. Hopefully that'll work. If you click on that, you should be able to get to the picture I was looking at. Yeah, if you look at that star, it has all those fusion layers, but you can think of that star as a sphere, right? And each color would be just a chunk, a cross-section of a smaller sphere. So that's what I mean by nested.
Oh, okay,
Does that make
got
sense?
it. Yeah, no, that makes sense.
Okay.
All right.
All right. Good. Yeah, could you imagine you trying to draw that? Like, I can't. It would be that would be a disaster. So we've got some answers, but remember, keep in mind, we're going to use the Earth. I'm going to take away the apple here, and we're going to use the Earth as one of these spheres. We can make another sphere, the smaller sphere, if we want, something like that. Whether they're spheres or solid or shells, they're each have the same mass m. All right, different radius, different sizes, but we've said that the object, no matter how big it is outside there. And what we said with our shell theory, the whole idea is that you can collapse any of these objects to the center. So because we're outside, you can actually collapse any of them to the center, and that will lead them to have the same distance, right? Regardless of whether the red circle or the Earth is bigger, right? You can see already here the effect of large or different distances. But if we shrink them to the same distance, right? The R's are the same, right? For every situation. The M's are the same, and G is the same. And therefore, you will have that actually all four forces are the same. Okay? All right. Good. So I took the picture of the attendance sneakily while you were all working on the problem. I guess it wasn't that sneaky. I'm not sure anyone cares except the school. But But yeah, so I think we're done for the day. I'll stick around for a little bit till 3:15 or so to answer any questions that might come up, but I'm going to stop recording, and we'll pick this up on Thursday.